For decades, quantum computing has felt like a distant dream. It was a fascinating concept, relegated to the chalkboards of theoretical physicists, the pages of science fiction. We spoke of its potential in hushed, reverent tones, always with the caveat that a truly useful quantum computer was still 20 years away. But something has shifted. That far-off future is no longer so far off. The theoretical has become tangible. Quantum computing is transitioning from a laboratory curiosity into a revolutionary tool. The breakthroughs are real, happening now, and their shockwaves are already beginning to reshape our world. The first great leap wasn't a quiet step, it was a thunderous declaration of arrival. For decades, quantum computing lived in theory. This was the moment it broke free, proving, unequivocally, that a quantum computer could do something, anything, that a classical computer practically could not. The benchmark was a computational wall designed to be unbreakable for traditional machines. This milestone is known as quantum supremacy, or the more diplomatic term, quantum advantage. The name sparked debate, but the meaning was clear. Google announced it had achieved this feat with its Sycamore processor, a 53-qubit chip controlled with unprecedented precision. This was about making qubits work together on a complex problem. The task: verify the randomness of numbers from a quantum circuit. For a classical computer to check this, it must simulate the entire quantum process. As qubits grow, that simulation's complexity explodes exponentially. There was no real-world application. This was purely about proving raw capability, a stress test for a new kind of engine. Sycamore did it in about 200 seconds. Google's paper claimed a leading supercomputer was estimated to need millennia. The claim was challenged. IBM argued optimized methods could cut it to days. But even this counterclaim highlighted the massive gap. The final score was minutes on quantum versus days, or worse, on classical. The point was made. This was the first concrete proof we had built a non-classical machine, operating beyond classical principles, and showing dramatic speed-ups. It wasn't just a faster calculator, it was a new form of computation. The result sent shockwaves through the scientific and investment communities. It silenced many skeptics and sparked new investment, shifting the conversation from if to how soon. For AI, it hinted at models recognizing patterns in chaotic systems, markets and climate. The experiment demonstrated control over the complex probabilistic systems that underpin advanced machine learning. This was the first evidence that quantum hardware could one day tackle optimization problems currently intractable for even the largest AI models. The quest ignited healthy global competition. Suddenly, it wasn't just one lab. Advantage claims emerged across platforms from teams in China and other startups. The race pushed builders to make processors larger, more stable, more capable, accelerating the entire field and setting the stage for the next leap. If quantum supremacy was about demonstrating raw power, the next two great leaps are about taming it. This is the shift from a spectacular lab experiment to a reliable industrial-grade tool. It's about achieving fine-grained control and building long-term endurance, turning raw potential into repeatable, revolutionary results. A qubit superposition is like a soap bubble, beautifully complex, but incredibly fragile. The slightest disturbance, a stray magnetic field, a tiny change in temperature, can pop the bubble. This collapse is called decoherence. It's the arch nemesis of quantum computing, turning a powerful calculation into random noise. In the early days, this happened in mere nanoseconds. The quantum state was gone before any real work could be done. So, scientists declared war on decoherence. They engineered ultra-pure materials, built super refrigerators colder than deep space, and constructed elaborate shields. The results were staggering. Coherence times shot up by orders of magnitude. Nanoseconds became microseconds, 1,000 times longer. Then milliseconds, and now, for some qubits, seconds or even minutes. Each leap unlocks exponentially more complex computations. This extended runtime is everything. It means you can apply more quantum gates, the fundamental operations of an algorithm. With short coherence, you can barely do simple arithmetic. With long coherence, you can tackle problems impossible for supercomputers, like simulating new molecules for drug discovery. This stability is what turns a lab experiment into a valuable tool. producing reliable answers and real ROI. For AI workloads needing billions of steps, this endurance is the foundation for quantum machine learning. But even with incredible stability, a second deeper problem remains. Errors are unavoidable. The quantum world is inherently noisy. While a classical computer might see one error in a quintillion operations, early quantum systems made an error every few hundred. It's not a bug, it's a fundamental feature of physics. Quantum errors aren't the exception, they are the norm. The solution is the third great leap, quantum error correction, or QEC. You can't just make a backup copy, because a fundamental law of physics forbids cloning an unknown quantum state. So, QEC uses an ingenious workaround. It encodes the information of one perfect logical qubit across a team of many imperfect physical qubits. They work together, constantly checking for and correcting errors in their teammates. The key milestone was achieving break-even, proving that a logical qubit could be more reliable than any of its individual parts. This was the moment QEC went from theory to reality. This breakthrough unlocks the path to large-scale, fault-tolerant quantum computers, machines that can run indefinitely, correcting errors as they go. This is what's needed for trustworthy results in high-stakes fields like finance and cryptography. But there's a critical warning. The same QEC that enables these applications is also what will enable a quantum computer to break today's encryption. It's a double-edged sword, and the race to prepare for both its promise and its peril is already underway. So far, we have focused on single machines. What if we could connect them? The next leap is laying foundations for a quantum internet. Not faster bits, actual qubits transmitted. Entanglement links qubits across any distance. Einstein called it spooky action at a distance. Measuring one influences the other instantly. This link becomes a quantum communication channel. Security is the flagship application. Quantum key distribution lets two parties share keys with absolute security. Any interception disturbs states and exposes spying. Detect, discard, and restart. Security by physics. Distances grew from meters to kilometers. The Messias satellite linked stations over 1,200 kilometers. Global quantum networking is now an engineering challenge. Many smaller machines can form a distributed quantum supercomputer. This democratizes access and accelerates progress. In a world of broken classical crypto, quantum networks protect finance, state secrets, and health data. Hardware is only half the battle. A powerful quantum processor without the right software has immense potential, but can't go anywhere. To unlock its power, we need instructions. That's where algorithms come in. This brings us to our fifth and final leap: practical quantum algorithms. Practical is key. We're not talking about theoretical algorithms for perfect future machines, but clever software designed to extract value from the noisy, imperfect quantum computers of today. Famous algorithms like Shor's and Grover's are incredible, but still years from being run at scale. The real action now is in hybrid quantum classical approaches, designed for today's NSQ devices. Think of it as a partnership. The quantum computer explores a vast landscape of solutions, and a classical computer analyzes the results. The quantum computer is the explorer. The classical computer is the analyst, refining candidates and steering the search. This iterative loop is the engine of near-term quantum advantage. A prime example is the variational quantum eigensolver, or VQE. It estimates the ground state energy of molecules to help design new materials and drugs. By simulating molecules, researchers can develop better pharmaceuticals or batteries before ever stepping into a lab. Finance is also leaning in. Banks are testing portfolio optimization and risk analysis, using quantum-inspired algorithms to explore vast combinations of assets, potentially uncovering strategies classical models would miss. And this brings us back to AI. By encoding data into quantum states, hybrid models may spot richer patterns or learn from less data. This could lead to breakthroughs in complex areas like medical diagnostics or climate modeling. So, how do you get involved? The world of quantum computing seems intimidating, but you do not need a PhD to begin. The barrier to entry is lower than you think. Here are 5 practical steps you can take today. First, learn the language. Understand core concepts like superposition, entanglement, and interference. These are the fundamental tools you need to follow breakthroughs. Excellent books and courses exist for beginners. Second, get your hands dirty. Try cloud platforms to run simple circuits. You can access real quantum computers from your laptop. Start with entanglement, the hello world of quantum, to build confidence. Third, think like a quantum developer. Look at your own industry and frame hard problems for quantum approaches. This mindset shift is your first step toward innovation. Fourth, connect with the community. Join the community to stay current and find collaborators. This field is moving at lightning speed. Speaking of community, what would you do with a quantum computer? Comment below. And fifth, stay updated with us. Subscribing is the easiest way to never miss a breakthrough. So let's recap. Supremacy, stable qubits, error correction, networking, and algorithms. These 5 leaps proved quantum is real, made it robust, and gave it practical work for today's hybrid machines. We are in the noisy, intermediate-scale quantum, or NISQ, era, an exciting, messy, and opportunity-rich present. The goal is fault-tolerant machines with millions of qubits forming thousands of stable, logical ones. The payoff will be immense, with breakthroughs in materials, energy, pharma, and finance. Imagine designing new drugs in weeks, or building financial models that mitigate market crashes. But with great power comes great responsibility. Our choices in design, security, and ethics will shape outcomes as much as any technical breakthrough. Like early computing pioneers, we are just getting started. We stand today where they stood in the 1950s, with room-sized machines and a universe of unknown potential. You've seen the 5 breakthroughs, the real proof, and the practical steps to get started. If this helped, hit subscribe, and then tap the end screen to watch our full breakdown of each leap. What problems will you solve when you can compute with reality itself?